Nathan will talk about guaranteeing accurate quantum phase classification with quantum convolutional neural networks. So, Nathan, the stage is yours.
Okay, thanks for having me. So, a lot of this work was done while I was at Friedrich Alexander University in Germany, but I've recently moved to Leiden in the Applied Quantum Algorithms lab. Yeah, so some acknowledgements. The stuff was funded, or this work was done also while I had an NLSN from Humboldt Stipendum or award, and was funded by European Union's Horizon 2020 grant. And this was done in collaboration with Michael Hartmann, Peter Zablati, and Leon Sanders. And there's a few papers that are shared on this stuff below. So I wasn't sure exactly how familiar people were with all this material, so I figured I'd start with some basics. So the basics are quantum mechanics is often just said to be linear algebra. Basically, certain mathematical structures in linear algebra give us some physical meanings. So we're talking about matrices, we're often interested in operators. These are Hermitian operators, Hermitian matrices. So they must be complex conjugate transpose. They must be self-adjoint, so they're complex conjugate transpose. It gives back the matrix. And often these have physical meanings. So often we talk about Hamiltonians with H, and as long as the Hamiltonian is some matrix that's self-adjoint, it's physical. So this matrix here is not physical because, for one, you have, this one, if you took the transpose, goes to 1 here, that's a 0. That should be a 1 or a 0. They should be the same. And while these might look the same, they need to be complex conjugate transpose, which is what this little, the complex conjugate, which is what this little star just means. So really, we have to talk about a matrix that looks a bit like this. And with these matrices, what we're often interested in eigenstates. So if H was a Hamiltonian, then the eigenstates correspond to the different energy levels. If you've done any level of quantum mechanics, you already know all this. But we can just say for any matrix, we can construct its eigenvalues and eigenstates and decompose any quantum state psi into its eigenstates with some coefficients. Often we might order these based on the amount of energy. So in here I have the eigenvalues. So the eigenvalues of these vectors. And that would correspond to the physical energy of whatever this state is. So here we have some mixture of all sorts of energies, and if we order them, it might look something like this. We can do this for any kind of operators. So we might have momentum, we might have position. In that case, these numbers no longer correspond to actual physical energies, but correspond to some other physical quantity. Often we want to simplify these so that they're normalized. Because when they're normalized, then we can always write the eigenvalue, any operator as its eigenvalue and vector and vector transpose. And this notation here, if you're not familiar with this, bracket notation, basically it's just, this is your vector, this is just a ket, which corresponds to the vector. And the other reason that we want these to be normalized is because when they're normalized, then we can get probabilities. And when we define probabilities this way, we can just say the expectation value of, say, an energy or position or momentum can be written as a weighted average over the different eigenvalues or eigenenergies, the corresponding momenta or positions. So this is all just basic maths. This is all maths, and this is the forms kind of like the basics of quantum mechanics. With this in place, we can start talking about transformation between states. So we have these vectors, psi, and we can transform them with just some other matrix U into psi dagger. So U is a unitary on 2 to the n states. So n is your number of qubits. And if we're thinking purely in terms of qubits, and I suspect other speakers will talk about other kind of configurations later, then the number of qubits defines the dimension of a matrix. So before we had a four-dimensional matrix, which meant that we're only talking about 2 qubits if it was a qubit system. If we're talking about more qubits, it becomes larger and larger, and that's why quantum mechanics is complicated, because every qubit you add means that the matrix you're working with is now 4 times as big, so double the number of rows and double number of columns. The only constraint that we have on these unitaries, on these transformations, so U, the unitary, is just that it is a unitary, which is defined by this. But often it might correspond to some sort of evolution by Hamiltonian. So we talked about this Hamiltonian, which was essentially the operator that corresponds to the energy of the system. And we might just evolve in time by some Hamiltonian H. And this is just the solution to the Schrodinger equation. Now, we might also talk about circuits. So rather than evolving by some Hamiltonian, we might have a bunch of gates. So originally, we might just have one big unitary, in which case this would be just one big blob here. So we put in some states, say all zeros, and get out some state psi. But in reality, we probably work more with smaller circuits. So we have lots of little gates. So these are 2-qubit gates, a bit like the 4x4 matrix that I had before. And we just evolve our system over D layers. And in this case, just one of these rows ends up looking mathematically like this. That instead of transforming by one big U, we transform it as the tensor product of many little U's. So many 4x4 matrices tensor producted together. And some special kinds of unitaries that we can have are the Pauli matrices. So these basically just split you between basis elements. So if we're familiar with the 0, 1 basis, that's the basis for the Pauli Z, and the X will flip you from 0 to 1 and vice versa. Y will also do that, but it'll add some phase while you're flipping. While Z will just add the phase, it won't actually flip things. But along with these kind of circuits, we can have measurements and feed-forward circuits. So for example, we might have 1 qubit. So each of these lines in these diagrams, I failed to say before, is a qubit. So 1 qubit goes through here and then gets measured in, say, the X basis. We could measure at any basis that we wanted. But in this diagram here, I just said X because we're going to measure in the X basis. So we measure that, and it's either going to be the +1 eigenstate of X or the -1 eigenstate of X. And we just take this as a classical bit afterwards. So that's what this double line here is if you can read it. We can also have controlled circuits. So rather than just having a unitary, we have it based on control. So this diagram here says that if it's in the -1 state, then if this qubit's in the -1 state, then we apply a Pauli Z operator onto this qubit instead. Control gates, these are also related to these feed forwards. So the idea would be that you, instead of doing a measurement after this on this qubit, we could do measurement beforehand and take this classical bit and tell the quantum computer, do we want to apply a Z or not, while retaining this classical bit. So that's something you can't do with a quantum bit, but you can do with classical bits. And all these things will pop up a bit later along with these kind of circuits. So the final thing with respect to these circuits is that we have this Heisenberg picture. So initially I talked about evolving the state forward in time. So you start with, say, this all zero state, and then you apply an evolution and end up with this state psi. Alternatively, we could say, I'm going to make a measurement. I'm going to measure the Pauli X at some point, and I can reverse that process. So instead of evolving psi forward like this, I can evolve X kind of backwards. So you can see that I have U dagger here instead of a U. And when I do this, I can think about the initial state and measure a different operator instead. So if I measure this operator on this state, it'd be the same as measuring this operator on the time evolved state. So these are just an alternative picture. So this is the Schrodinger picture, and this is the Heisenberg picture. And if we're looking at the Heisenberg picture, then we get some special times gates, which are the Clifford gates. So if we're measuring an X, Y, or Z, then if you evolve by Clifford Gate, you get back twice X, Y, and Z. And this actually makes things really simple because if you're trying to simulate Clifford circuits, at least if you start in a certain state, then all this simulation can be done classically. So I talked a bit about eigenstates before. Often we're interested in ground states. So the problem is, let's say I have some nice Hamiltonian and I want to find the ground state, or I want to find some low lying energy states. Why do we want to do this? Well, one thing is nature often likes low energy states, so we don't need to worry about high excited states often, or at least not very excited states. Often, as long as the system's cool enough, we only need to study the ground state or the low lying states to fully understand the dynamics of the system. So for that reason, we might want to prepare ground state. We also know that if you want to find the ground state or low lying states for some type of Hamiltonian called K local, then it's QMA hard. That just means that it's going to be harder than pretty much anything you can do with a quantum computer. So even just finding ground states or preparing ground states would be pretty much impossible even given a quantum computer. So it forms a very complicated problem that should be able to give us a lot of useful, that could allow us to learn a lot of stuff about the system, or could allow us to solve very complex quantum problems, very complex problems. And also any quantum circuit can also be written as the ground state of a K-local Hamiltonian. And sometimes we may just want to predict the properties of graph. And all this stuff is just going to be some of the examples of what you might want to do with a quantum computer or with quantum machine learning. So one way to solve this is adiabatic state preparation. So we start with, say, the all plus state or the all zero state, and we want to evolve this to the ground state. And all we need to do for this is we need to know some Hamiltonian, which starts in the Hamiltonian, which has the all plus state as its ground state, and transforms continuously to some Hamiltonian, which is our Hamiltonian of interest. So for example, if we have some parameters H1 and H2, we might have the all plus state here, and we can essentially draw a line in this space of Hamiltonians from our initial state to our final state, which is the target A or target B, or maybe even target C. But I'll get to why that might not be the problem, might not be the case in a moment. And we just evolve with the Hamiltonian here. We evolve with some unitary based on the integral of the Hamiltonian over time. This has to be time ordered, and that should be a plus, sorry, not a zero. And we get some error that depends upon the lower line state. So between the difference between the ground state energy, E0, and the first excited state. And the inverse of that difference tells us how much of an error we get in this approximation to the ground state of some given Hamiltonian. So we can evolve from the ground state of this Hamiltonian all the way to the ground state of this Hamiltonian by just evolving over this path of Hamiltonians here, or this path here. And I've drawn this diagram here. So this line corresponds to when this difference becomes basically zero. And we wouldn't be able to evolve from this state to this state here, if that was the case. And there are many ways to implement it. We could use some lasers or any other analog instrumentation, or we could do some equivalent gates and circuits. And I believe there'll be a talk later, which will talk about multiple, about the different ways you could implement unitaries in quantum computers. The last thing I'll talk about is a little bit of quantum errors. So instead, so instead of evolving from the state psi under some unitary u, we may pick up some errors. So we evolve to zu rather than. Normally, coherent errors might look something like this. So it's no error plus a little bit of error here. And if we're talking about quantum computing, then we use additional qubits to detect and correct these small perturbations. Again, we can take these Pauli matrices I showed before are interesting because we can decompose all unitaries into Pauli errors. which basically means that if we know how to correct for Pauli errors, then we know how to correct for all of these kinds of errors. And in fact, certain error patterns dominate reality, and that's how this quantum error correction procedure works. So for example, we might just need to correct Pauli X and Pauli Z. And if we really want to, we can think of adiabatic state preparation as a kind of error from starting reference states. Now, this isn't normally a typical way of thinking about it, but this is what we're going to use later in this talk. So I've made a bit of a jump here for quantum errors, but all these QCNNs that I'm about to talk about, an original way of thinking about them is they are a way of correcting errors. So correcting from a perturbation away from a reference state. And as I said, we have the Pauli strings. So these are just products of X, Y, and Z. And all operators can be written as sums of Pauli strings. So like some decomposition here. And if it was, say, dominated by, or if it was small perturbations from a Pauli X error, then we might have the unitary with an error is a sum of the proper unitary, unitary with a single X, unitary with two X's, with some coefficients out front. And as long as P, the probability of getting this error, is pretty small, then we basically might only need to worry about the first couple of terms in the expansion. If we instead say that the error or the unitary is based on, this is a different use of what we have here, is based on the Hamiltonian that we were talking about before. So for example, this Hamiltonian here, then instead of talking about Pauli X's, we can talk about the terms in this Hamiltonian. And we can think about the errors as, say, a single X or double X or ZXZ. Okay, so that's just a whole bunch of basic details and in some sense kind of random details, but I'm going to make use of each of these as I talk about my work, these quantum convolutional neural networks. So what is a QCNN? What is a quantum convolutional neural network? So the key QCNN that we're going to talk about is the one here. The basic idea, and it comes from this paper here, Hong et al., is that we're going to take a phase diagram. So we're going to have some Hamiltonian like we had before with parameters H1, H2. And each of these points in this phase diagram corresponds to a Hamiltonian. And for each Hamiltonian, we have a ground state. We have a low line, the minimal energy state. And what we want to do is we want to take the state, we want to run it through this quantum circuit. And at the end, we'll make a measurement on this quantum circuit, and it'll either be, say, +1, which tells us we're in something called a SPT phase, or symmetry protected topological phase, or it's going to be a 0, which means we're not in that phase. So in this case, either paramagnetic or an antiparamagnetic phase. And this circuit is applied L times, and in each of these layers, we get less and less qubits. So you can see here that we've made a measurement of these. We have these two qubits going in, but we're going to measure both of them out. Then we apply some feed forwards, and we had, say, 7 qubits coming in here. We're left with 3 qubits at the end. And the idea is that as we apply more and more layers, we start off with a really crude estimation of whether we're in the SPT phase or not. So this is just one slice, say about here, I think. And if we do one layer for the QCNN, then we see a line that looks like this. So we can kind of see that it's detecting when we're in the SPT phase, but it's a bit of a yes. But as we increase the number of layers of the QCNN, it becomes sharper and sharper until eventually you see it's essentially a top hat function. And this top hat function tells us we're in the SPT phase, which is what we see here. That we see it's very clearly in the SPT phase, or it's not. So why is it called a quantum convolutional neural network? Well, it comes down to the structure and a bit of a misnaming. But the idea is essentially that a QCNN can be written as a fully connected layer here, plus some convolutional pooling layers. So we got L repeated layers, and that should start with L instead of D. And we just keep repeating a pattern that goes on and on. And this pattern we're made up of 2 convolutional layers and 1 pooling layer. And the basic idea is that these convolutional layers will take us from the all plus state to some reference state, which depends upon the Hamiltonian. And we choose these convolutional layers to be Clifford. And that's just to make things simpler for some of the calculations later. But we're going to have a lattice of qubits here. So each of these dots corresponds to a qubit. And we're going to have one of the convolutional layers will act on all the qubits, while the second one will only act on these target qubits. These are the qubits that will remain in the next layer. And that describes these first two, this orange and this red region here of the circuit. Then what we do is we have a pooling layer, which does a lot of the complex calculations and does this kind of error correction I suggested earlier. So what it does is it takes these controls, and you see that we've only got controls and measurements on a subset of the qubits, and then it applies some evolution, some unitary, say, poly X or poly Zs onto the target qubits. Now, this circuit diagram, this example here, this is all completely fixed. There's no training involved, even though we call it a neural network. This is a pre-designed neural network based on some understanding of the system. Oh yeah, and the fully connected layer also has its own convolution part and another bit. But just so everyone's aware, for all the QCNNs that I'm going to be talking about, they're all going to be fixed. They're going to be not trained, but they're going to be designed based on our understanding of condensed matter, of ground states, of Hamiltonians. So what's this problem, or what are we trying to solve with this? Well, we kind of saw it already, that we're trying to detect different phases of matter. So for example, you're familiar with solid, liquids, gases. For quantum mechanics, we get something a little different. We might have temperature, but we also have these quantum critical points. So a bit like we have the phase transitions in this diagram here. As we change from an ordered state to a disordered state with some parameter P or parameter H and the other Hamiltonians not shown, we transition from one phase into another. And the kind of example that we're working with is this Hamiltonian I talked about here. And we have this FBT phase, ferromagnetic and antiferromagnetic, which we already saw in the previous slide. So the basic task is, can I take the ground state of a Hamiltonian that corresponds to one of these points and tell you what the phase it comes from is, whether it's the SBT phase or something else. So that's what all these QCNNs are going to be that we're looking for. Now we have these lines which correspond to phase transitions. That's basically when the ground state switches or becomes really close with the first excited state. So this might be your diagram here, the ground state energy, first excited state, either they swap or they become arbitrarily close. And that leads to measurements which might jump or be discontinuous. So the basic idea is that we're looking for these discontinuities, and this leads to massive changes in the state. And we can also talk about this fidelity, but I won't go into that just because we're running out of time, I think. Yeah, so the basic idea is that when we talk about these phase transitions for these diagrams here, as we cross this phase transition, we see a rapid change in the behavior of the state. And that's why we classify different phases. Well, that's why we classify these different quantum states as different things. So say an ordered state or disordered state. Or if we're familiar with more classical stuff, solid, liquids, gases. And the last thing I need to talk about is symmetry protected phases. So an alternative way, rather than talking about it as this crossing, this band gap closing, this discontinuity, we talk about phases and phase transitions based on quantum circuits. So we say that to go from one phase to another, we need a long enough quantum circuit. If we have a short circuit and we start in one phase, then we're going to end up in the same phase. For a special class of states, we have these symmetry-protected phases. So symmetry-protected topological phase that I talked about earlier. And if we break the symmetry, so we have certain constraints on each of these unitary gates. that means that makes this circuit symmetric. If we break these constraints, then we may go from phase 1 to phase 2. We may change the phase with a short circuit. It's a bit like saying that we need to say stay at a fixed pressure. If we stay at a fixed pressure, as we're going along this line here, we transition from the solid to the liquid and liquid to the gas, and we'll definitely see a phase transition here. So we're going to have some complexity arising. If we could break the symmetry somehow, then we don't need to go through the phase transition. We can kind of jump up around here and not have to go through a boiling transition. These symmetry protected topological phases also have an order parameter, which allows you to detect it. So if you measure this operator here, which ends up just being, if we can measure this operator here, then we could detect if we're in a symmetry protected topological phase or not. And for the kind of model that we're looking at, this is the string order parameter of interest. So how are we going to construct this? The basic idea is that we have some unitary, and we think about this as an error. So this is a perturbation away from this reference state. And we can think of decomposing this as sum over errors. And what we're going to do is we take this error, we have all the terms, all these errors that this unitary is generated from are the terms in the Hamiltonian. So this Z, X, Z, this X, and this XX. And we're just going to get that we introduce an error, which is a sum of products of these error terms. And the basic idea is, first of all, we choose the fixed point, and we choose the convolutional layers based on this kind of rule that I mentioned before. This is how we build this QCNN. And this is basically the same QCNN as before, but without a little bit of error correction, fully connected layer. Then we do some pooling. So a lot of the complexity comes in this pooling layer. So we say, if I have just a single error, then I want to be able to remove it with the pooling layer. And if we have two errors, then this pooling layer should combine them and either remove them completely or combine them to a single error. So if we had, say, two X's, this pooling layer, or this full layer here, the convolution plus the pooling, will end up taking two independent X's and combine them together into a single X or a single ZXZ, or this pair of neighboring X's here. And these are all the rules that we use to construct these QCNNs. And it's based on something called renormalization theory, but that's way too much for this talk, so I'm not going to talk about that. So how do we start to see this? So this links back to this error correction. So how does the circuit do a kind of error correction on these kind of errors here? So if we have this ZXZ error, we have this circuit. And if you're familiar with Clifford gates, so these are controlled Z gates here, these two dots with a line between them. We put this X through here, and because of this convolutional layer, it ends up essentially eliminating this Z here and this Z here. And now this X, and I'm not sure how well this line's coming through, but basically can pass through because a poly X is not going to change. This is just going to add a phase, so it doesn't interact with these control gates. So it's just going to be measured out, and we can ignore it. So we can see the ZXZ error will just get completely eliminated. So that's good. That's one of the kinds of errors that we can get eliminated. If we just had an X instead of a ZXZ, we get something a little bit more complicated. So now there's Zs appear here and here. So we now have a ZXZ. And as we go through this Z here passing through this control gate will introduce the second Z here. So that will eliminate this Z on this remaining qubit. So this is the kind of error that we're talking about before. So it eliminates an error here by measuring out some of the control qubits. So this error was spread onto here, but gets eliminated by this. So we just have an X here and a Z here on the measurements. So nothing's going to go onto the next layer. So it's all good. We can look at it a bit more complicated if we shift it. We just get something similar. It becomes a bit longer because we've now got this second convolutional layer. But here, if we look at just the single X is eliminated. by having this pair of x's here, because this is a controlled gate. And then again, the two z's that just appeared get eliminated and nothing passes through to the end. Now for this ZXZ, we get slight violation of the rule. The ZXZ itself can pass through to the next one because it's what this reference state is. So I can go through that in more detail later, but this is one exception to the rule that I gave before. If we have these two x's, we can go through again, and we see that these two x's basically look like two copies of this in this region here. But if we have the x's in the right spaces apart, then most of it looks the same until we get here. And now these two z's end up giving us extra x compared to what we'd have if we just had this one or this one independently. And then this single x goes through here. So we take these two x's, and the output of this circuit just gives us a single x. So this is just the kind of computation we do with this error correction procedure. Well, this is the way of thinking about these QCNNs as error correction. This is how this QCNN is constructed as opposed to training it. Yeah, so there's another nice structure that has to do with this recursion relation. I'll just skim over it, but the key thing here is that we have this recursion rule, and that we can write the measurement. So the resulting operator that the QCNN is going to measure as a product of L and R, which are separate regions here. So for example, if this is our X, then L will just be on these qubits here, and R will just be on these qubits here. And if we want to, so we have this recursion relation, and we'll use this in a moment to prove some things about this constructed QCNN. So I've talked a little bit about what's been done rather than what I've been doing. So this is the original result. There was a separation between the SPT phase and paramagnetic and antiferromagnetic phases using just some constructed QCNN. This has been done experimentally on 7 qubits in this paper here. There's been some further work looking at two-dimensional systems, so looking at something based on the toric code and perturbations of the toric code as your Hamiltonian rather than the Hamiltonian that's already shown. I won't get into what the toric code is, but it's fairly common, fairly familiar. What happens when you have errors? So if you have physical errors that come from, just say, thermal fluctuations or other sources of error, there have been studies about, can we use the QCNN to capture or to still detect this, to get a nice sharp phase transition when we have these kinds of errors, and other stuff where we look at multiple symmetric protected topological phases and showing separations between them and doing classifications for multiple phases rather than SPT phase and a trivial phase. And along with this, there's been a bunch of work done with trained QCNNs. But I'm not going to talk about that in this talk. But now, in the last couple of minutes, so I'll very quickly try to get through the idea. The idea is basically, the thing that's missing is you see that these don't actually agree with the lines of where the phase transition should be. It's just roughly approximate. It's even worse when we only have 7 qubits. But the question is, can we prove that this is exact? And the basic idea is to say that if we have some reference point and we have some other point in the phase, can we prove that the difference in the QCNN output is going to be pretty much zero in some way? So the basic idea here is we're just going to split this into, we're going to take these parts, this adiabatic state evolution I talked about before, and we're going to split this into multiple steps. Then what we're going to do is we're going to think about, say, the perturbation from this, the difference in the expectation here to the expectation here. And we're going to bound this change in expectation value, this change in expectation value with small perturbation in this parameters H1 and H2. We do this with Chebyshev inequality. So we can compute the variance of some random variable, we can place a bound on the probability that this random variable is going to be different from its expectation value. For quantum states, we can do this for some operator with some state, and we're going to take it over some set of states S. And what states could we be interested in? We could be interested in these short circuits, because recall the phase transition, you can't go from one phase to another using some short circuit, so using some constant depth circuit. So the basic idea of proving that these QCNNs actually work as they seem to work is basically we're going to bound the expectation value of the QCNN output from its the change in the QCNN value from its expected change over the set of all possible states that you could prepare from some fixed initial state, which I called the reference state there before. And this ends up giving some probability distribution of what the expectation value could be. And we see that it becomes very concentrated, but to be proportional to the variance, or the square root of the variance. So going through that equation before, I'll just very quickly skip, the change in the expectation value will be bounded by essentially something that's proportional to the square root of the variance of the commutator of the QCNN output with how the Hamiltonian changes over that small distance, plus something that's negligible as we take n to infinity. And what we want to show is we want to show that this variance goes to 0 as L goes to infinity. So the number of layers the QCNN goes to infinity. So we can make use of a whole bunch of Weingarten calculus. I won't go through all this, but we can do a bunch of maths, and I can go through this if you have questions. And we end up with this result for the variance. We show that the variance decays as long as we preserve the symmetry, but if we break the symmetry, then it goes. But because we only are interested in seeing what happens as when we look at the variance for perturbations that preserve the symmetry that I talked about before for the SPT phase, then this shows us that this bound here should basically go to 0 as long as we can take L to infinity, or with sufficiently large probability, it should go to 0. So sufficiently large probability is only true probabilistically, but must be true of all possible paths when we do this. And there might be some small region around here, around the reference state, and this needs to behave typically. If it's non-typical, then the approach may fail. But basically, using these two ideas, that the variance decays to 0 as we take the number of layers to infinity, and studying around the reference state and how the QCNN behaves around that, we can construct a bunch of other QCNNs. So the key question was, does this approach prove or explain why the QCNN will match the QCNN output does do this phase classification properly, this classification task. And we can use these insights to essentially generate a whole bunch of random QCNNs, which aren't trained, but they're just randomly sampled from a set of all possible, a set of possible unitaries based on these rules, these two rules about the variance and behavior around the reference state. And we can see that the original QCNN, which is given in cyan here, is basically the same as the randomly sampled QCNNs. So these are 20 randomly generated QCNNs. And we can see that pretty much matches as long as some parameter R is bounded. And as we decrease this band, as we go away from this bound, we see that the constraint becomes looser and looser until essentially it won't tell. So to conclude, that's the basic idea. That's some introduction to these QCNNs and some work that I've done with proving that these QCNNs do what they say they do. So some next steps would be basically, can we apply this approach to other condensed matter models? Can we add for training? Can we apply these ideas of studying things probabilistically and using these relationships between this guarantee on relationships between states that are within one phase to prove or place stronger bounds when we talk about training and building QCNNs that can be trained? Can we deepen this understanding of these probabilistic bounds that I talked about before, and very, very briefly, unfortunately? And can we apply this to other classification tasks? So all this stuff is about phase transitions and phase classification. Could we take these ideas and apply them to other classes where we want to classify some sort of quantum state? And can we deepen our understanding of why quantum circuits or quantum neural networks or quantum machine learning might work based on these kind of ideas? So I'll end the talk with questions. I think we have maybe 5 minutes. And hopefully that might give some ideas for the remainder of this workshop.
Okay, so many thanks to the speaker. Thank you, Nathan. It was great. And we have some questions in chat. Let me see.
Yeah.
Maybe Nathan, you see this question also.
Unfortunately,
oh,
the Zoom keeps appearing on my over my slides.
Okay, so I'd like to ask a question. Do
Yeah.
we know a point? Do we know a point that at which it is not worth to have some error correction? By this, I mean the point at which the error correcting part of the circuit adds enough noise to run the whole circuit.
Are we talking about? I'm guessing we're talking about this kind of view of the QCNN as an error correction protocol. So if I'm getting it correctly, so the idea is that if the circuit is so if there's only a few errors, then we do this error correction procedure correctly. But if we get too many errors, then basically all these errors end up just introducing pure noise. So there's a kind of transition, so a kind of step function from where we can perfectly correct the errors if the Hamiltonian has changed only a smaller bit away from the reference state. So I forgot to mention the reference state is when h1 equals h2 equals 0, so it's just this part here. So if these are very small, then we correct the errors that appear. If these are very large, however, then basically the errors just create this kind of mess, this disordered mess. And we'll get many more interactions like this. And we might find that you might have n errors initially, but if there's too many of the errors or they're too dense, then it goes from n errors to a larger fraction of errors on the remaining qubits. And this essentially is the kind of trigger for a phase transition that we can't correct for these errors, and that's the interpretation of this QCNN. But we have too many perturbations moving us away from reference state, and that leads to just too many errors. The circuit can't compensate for all the errors and would just cause the number of perturbations to explode. Is that answering the question?
Okay, thank you for the answer. Next question is from the audience. Okay, please go ahead.
Can you hear me? Oh. Okay, so I
Yeah,
have a few questions. So first, it's about the error correction. I would like to know, like, could you tell me, like, how the distance of these codes behave in your example?
Okay, so the first thing to think about is that this is not really an error correcting code. This is motivated by the idea of error correction. So it would be it would be incorrect to think about this as an error correcting code. It's so the sense of a distance doesn't really exist in this case. Really what it is that we're trying to do a phase. We're trying to recognize these phases, and if you really wanted to, you could think of the reference state as a code, but that's probably not the most useful way if you're trying to do this classification task. So it's not really related to that. It's not related to quantum codes. It's that this idea of error correction gives some insight as to how the circuit was built and how the original proposal, how this Kong et al. Paper talked about it. It was based on renormalization theory and about error correction. And the idea is essentially the error correction just gives us a vague idea of why we might see this kind of step function where it goes from +1 in this red region here to 0 in the other two regions. Because we see this nice sharp transition. And that's a bit like what you see when you take a quantum error correcting code and you take the number of qubits or the system size to infinity. We see that we can completely correct it up to a certain threshold, and then it drops down to where it's just completely random noise. So these are separate, but just mathematically similar, I guess, is maybe the best way. So I can't really give you a distance.
Okay, thank you for the question. May I have the second question? So you said at the end of your presentation you want to add the training part. So do you have like some perspective how it would your model behave with common problems as a barrow plateaus in optimization of parameters of such as circuits?
So QCNNs have been shown not to have barren plateaus. So you wouldn't run into problems with barren plateaus there. There have been studies that have looked at can we train QCNNs, but the kind of question that I'm asking here is, could we use these insights to kind of give a guarantee about how well the trained QCNN works, or prove that the trained QCNN will work up to some sort of threshold, or give us some guarantees on how well training will work, rather than just saying, okay, let's train it and let's run some numerics. Oh, it seems good enough.
Okay, yeah, that's true. Okay, thank you very much.
Next question.
Thank you for your talk. And I have a question. Do you have some intuition on which classification task this model could be fitted? Because today I also talking about some classification tasks, so it's quite interesting for me.
The main classification task I can think of is essentially classifying which phase of matter you're in. To be honest, I haven't thought deeply about what other classification tasks this could be mapped to. I think the real thing is you need if you think about the classification task of a set of quantum states, and they can be put on some diagram here, like this H1, H2, and you have some guarantee that, say, you can compare one state from another state, or some guarantee about the relatedness of things within one of the classification phases. So if you're classifying it as SPT phase or non-SPT phase, you have some guarantee that all states in the SPT phase are related in some way, and they're separate in some other way from the non-SPT phases. That was this idea of long versus short circuits. So if you're in the SPT phase, then you compare the SPT phase, or you compare one SPT phase state from another using a short circuit, and this is all connected to this adiabatic state preparation. We can take adiabatic state preparation, write as a short circuit or sufficiently short circuit, and guarantee that you can approximate any other state in the phase relatively well. But if you need to cross this phase transition, then you need a long circuit. And you have a guarantee that essentially you need a long circuit to go from an SPT phase to a non-SPT phase. That's probably the best connection I can give you. If you can exploit some property like that about how in your classification task, then you might be able to adapt these kind of ideas. But maybe we can talk a little more later, or I might get some ideas from your talk.
Okay, thank you.
No more questions. Okay, one more question here. Maybe the last one.
Hello, yeah, Thibaut here. The talk was great, thank you. I would like to make just a comment on the analogy you made between phase transition in electronic system and the one in solids and liquid and gas. I think these are very different systems, and it's difficult to compare them, especially because by this you assume somehow that the symmetry would be the same when you change the phase in the electronic subsystem, while in the experiments we start to see that it may not be the case. And so speaking about phase transition in solids, I guess you rather wanted to show intuitive picture here. But
Yeah, you're talking about how I was saying that you can kind of get around the phase transition liquid gas by going up around here. Yeah. No, that was purely just to get some intuition across.
Yeah, that's why comment on it's more detail for the scope of presentation, but it's more on my specialty, so that's why.
Yeah. No, this was just to get some intuition across because everyone knows solid, liquid, gas, and you've probably come across supercritical. And if you're trying to wrap your head around, okay, what's this thing about you can't cross a phase transition unless you break symmetry? This at least gives you a very crude, very rough idea of something that looks vaguely similar, at least if you're squinting hard enough.
Okay. I think we will send you an email with some presentation that we can discuss later. Thank you.
Yeah, looking forward to it.
Okay, so thank you very much for your very beautiful talk and for the discussion. And let me thanks to the speaker once again.
Welcome here after a coffee break. My name is Michal Belina. I'm a member of Quantum Computing Lab, and my role here is to introduce our next speaker, who is Jiří Tomčala, sitting over the computer there. And today he will be speaking about phase gender recognition using quantum machine learning on NVIDIA CUDA quantum simulator. So Jiří,
yeah. Thank you. Thank you for introduction. I hope everyone can hear me. Maybe here in the room also. Yeah. Okay. So maybe I will start with some general introduction to quantum machine learning. I'll say some general facts, and it's just that we can it's all so things that are quite known, but I just say this introduction as that quantum machine learning is a research area that explores the interplay of ideas from quantum computing and machine learning, and that quantum computers can speed up the time it takes to train or evaluate a machine learning model, which is the most important feature of this quantum machine learning techniques. And this feature enables creation of on much larger scales in the future. So these larger models, they could be possible thanks to the quantum machine learning, then can be more complex, and they can solve more complex tasks. So bringing them closer to the human brain, for example. Yeah. So, and there's another advantage that these advantages that while many quantum algorithms like Grover's or Shor's require a fault-tolerant quantum computer to function, the quantum machine learning can be meaningfully implemented using already existing quantum computers. This is important, of course. So since we live in this noisy intermediate quantum era, this possibility makes this quantum machine learning one of the main directions of using quantum computers today. So these are all reasons why we are dealing with quantum machine learning. So maybe because the topic of my talk is a practical example of phase gender recognition that simulated on NVIDIA CUDA quantum simulator. So I will say a few words about this simulator. So it's interesting to know that this simulator is QPU agnostic platform for accelerated quantum supercomputing, and it's open source, and it's orchestrating the hardware and software needed to run useful large-scale quantum computing applications. So it streamlines hybrid application development and promotes productivity and scalability in quantum computing. So it offers some unified programming model designed for hybrid settings where CPUs, GPUs, and QPUs work together. So it contains also programming in Python and C++, and it's not necessary to have GPUs to use this software, but some components are GPU accelerated. You can use it, by the way, on your laptop. It's just a Python, it's a Python package, but you can achieve much bigger speed up if you have these GPU cards. I mean GPU cards from NVIDIA in this case. So it enables the straightforward execution of hybrid code on many different types of quantum processors, simulated or physical. So you can simulate some on the software. You can simulate some specific QPUs, and there is also a possibility to if you have access to this, if you have online access to this through the cloud on these QPUs, you can run it on these physical QPUs thanks to this software. So this software extends simulation tools far beyond the NISQ era and charting the course to large-scale and error-corrected quantum supercomputing. So maybe there's a nice picture showing this speed up. If you have GPUs on your computer, so you can achieve up to 2,500 speed up on 26 qubits. I was able when I was experimenting with this software on my laptop. So thanks to the fact that I have a new laptop with 32 gigabytes, I was able to experiment with 29 qubits, but I don't have the GPU, so I didn't measure any speed up. But on the infrastructure here in our supercomputing center, we have NVIDIA cards here. So I can confirm that when we experimented with this software on these NVIDIA GPU cards, we achieved a really big speed up. Maybe not 2,000, but it depends on application, of course. So it's really good if you have. So it's really useful software if you have this GPU cards. Well, there's another interesting feature of this software, and this is so-called that it's this so-called quantum kernel function possibility. I would say I would say that this is not a quantum kernel from the support vector machines methods. This is something different, but it's the same name. But it means here in this software, it means that you can define these quantum kernels as a function that are executed on quantum processor units or simulated QPU. What is the advantage of these quantum kernels? That it can combine classical functions to create quantum classical clock applications that can be executed on heterogeneous systems of QPUs, GPUs, and CPUs to solve real-world problems. So it's really it's really good for if you need to run some hybrid quantum classical application. So every quantum circuit is a kernel, but not every kernel is a circuit. So quantum kernel can be built up from other kernels, allowing to interpret a large quantum program as a sequence of subroutines and of subcircuits. So moreover, since quantum kernels are functions, there's more expressibility available compared to a standard quantum circuit. For example, if you use some Qiskit or CIRC framework, it's not so flexible if you want to do some programming structures. So it's possible not only parameterize this kernel, so it's good for parameterized circuits, we'll talk about later, but it can also contain classical control flow statements as they are if, for, while, and so on. So and classical computations such as additions, multiplications. So conditional statements on quantum memory and qubit measurements can be included in quantum kernels to enable dynamic circuits and fast feedback, particularly useful for quantum error correction. Maybe I should say here that also Qiskit framework it's also possible to create dynamic circuits, but here in this software it's much more easier and more and the faster if you have these GPUs. So I think that's enough information for this NVIDIA CUDA quantum simulator, the software. And I should say something about how the hybrid quantum neural networks look like. We have the first picture here, and maybe I will say something. Maybe something about here. So we can see here. This is our classical part. Yeah, and here, this is the quantum layer. So you can put quantum layer as the instead of a classical layer here. You can see that this is classical layer. There are some neurons, right? And mainly we use here linear regression layers that are reducing the number of inputs to number of parameters of this quantum layer which is implemented by some variational quantum circuit that I will talk about it later in the next slides. And then after measuring this variation quantum circuit, you calculate some cost function where you're looking for, as you can see here, we're looking for some minimum of this cost function, and if we are not in the minimum, we calculate some gradients and update parameters of variational quantum circuit, and run it again and measure it again till we find the minimum we are looking for. So in this way, we can learn something. This hybrid quantum neural network, and maybe could be more obvious from the next slide. It looks like this, that we have, as I already said, that we have a parameterized quantum circuit, or we can say variational quantum circuit. It's the same. So this is here, and we, as the first we initiate some theta 0 set of parameters, for example, and then from the beginning. But if we have the classical layers here, or maybe one layer, for example, then these first initialize this initialization of the first theta parameters is output of these layers. Okay, I will show you in the practical example in the next slide. But as I said, we run this variational quantum circuit, then we measure again the output and evaluate this cost function, and using classical optimizer, we update these parameters theta by some step, by some, and this step, it depends on so-called learning rate. Which is, as we will see, it's really important to training and evaluating. So this learning rate is the classical optimizer. So this is the principle how it works. This variational quantum circuit, and we can take a look how these variational quantum circuits can look like this here. So maybe you saw some variational circuit in the talk of of the previous speaker. So there are a lot of combinations you can create this circuit, and maybe I should emphasize that in the beginning, there is almost every time there are zero states, but the input of this quantum circuit is in fact these parameters. So it's these parameters theta, or maybe phi, or it doesn't matter how you denote it, but and then every time, but if you need more parameters, it's important to have some entangled part of this circuit to somehow entangle these two qubits together, and then you can use another parameters to rotate the quantum states. And of course, it depends on how you compose these rotational gates. Sorry, how you compose these rotational gates. Mainly, it's enough to have rotations about axis x or and axis z. So these are enough. It's enough, because if you have the quantum state, you need two rotations to achieve any quantum state on the box sphere, for example. So these two are enough. Maybe sometime it's also possible to use only maybe rotations around x, for example. I'll show you this later on this on my specific example of this phase gender recognition. But then you should put more entangling layers. So I think this is good time now to show you the results of our experiments with various types of variational quantum circuit structures in this hybrid quantum neural network. So maybe first experiment we did is using 2 linear regression layers and 4 qubit layer with 16 parameters. So it's you can see that we used 1,434 faces. There are 717 male faces and 717 female faces, and it was our training and test set. So maybe I can a little bit zoom it in. So we put it in this. We needed to use two linear regression layers to reduce these parameters because we had 100 times 80 pictures, so there are 8,000 pixels. So we needed to linear regression layers to lower this number of parameters to 16 to put these parameters as a parameter into these spin gates Rx and Rz. So we were quite successful, and we measured we train this hybrid network, and we achieve this learning curve. So we can see that as we can suppose, it's test curve or test learning curve of test set is maybe a little bit less precise because these are photos that are not being trained. This neural network has not been trained by to these photos. So, but it's possible to use to create a variational quantum circuit with more parameters, but we needed we needed more qubits for this. So it looked like this, but still we needed to use two linear regression layers here. But you can see the learning curve was a little bit different, but almost the same. So what is the advantage of these more parameters? Because we have 32 parameters, as you can see, is that the main goal of this hybrid quantum neural network is to replace all classical part with quantum part. So these are so-called little steps to achieve this goal. So we made sure that even when we use these 32 parameters, it still could be learned this neural network. It can be learned this face recognition. So, but we started in this part. We started to experiment with a learning rate values. I was talking about in some previous slides, and maybe it could be interesting to show you that we try the very same circuit. We try to learn this to do this train, set, and tested using various values of learning rates. So I'm showing in the next slide the result. I think so. Yeah, that's it. So we can see that from this learning rates experiment, you can see that if you have too big learning rate, it's not good. Of course, if you have too loud. So you can, in this way, we found that the ideal learning rate was about maybe this or maybe this 1,000. Yeah. So if you have some too big learning rate, it's a well-known thing from the classical neural network, of course. So if you have the too large or too big learning rate, you will get to this problem that you cannot find. That you cannot find the optimal solution or optimal. Well, I can maybe maybe show you the maybe if you minimize the some function, and you are, for example, here, so you can see the gradient is this negative. That means that the minimum is in you should add the value. So you add the value that it depends on learning rate. So if you do too big step, you missed your minimum, and then you go back, because so you go back, and then you go back, and then I'm back. So you never get the minimum. So that's a problem if you have that's why we can see here. You can see here this that we don't know. It was not precise enough. It was just about 70% here for the it was to be. So we found out that the optimal value is 1000, or maybe this. And then we're trying to reach our goal with doing experiments with more parameters. So I can see. So we were able to compose much bigger variational quantum circuit with 64 parameters, as you can see. And then in this case, it was enough to have only one classical layer. And we can see that the learning curve is not so ideal on the beginning, but at the end of the maybe 70 epoch, we achieved again quite good precision, but 90% here. It's 90%. So it's possible. So we success with this hybrid network with 64 parameters, 64 quantum parameters. But we realized that here on the beginning there's some delay in training. So we experimented more, and we trying to sorry, this is not what I mean. We trying to replace these spin gates in a different manner, and we try to put more entangled layers here. So I'll show you on the next slide how it looked like the. Yeah, I'm in the end. So there's our last two examples. So you can see that when we split this circuit, this variational quantum circuit, we realized that the learning curve was much more slower. Yeah. So the problem is that we put these Z rotations in this manner. So in fact, it has no meaning for this learning. So because if you see the last slide from the last experiment, you can see that if we replace these Z spin gates with only X gate spin, you can achieve much better training curve. So it's much more faster, or much more. It's faster, and it depends on how you set your entanglement layers, how you set your how you set your learning rate, and what kind of spin gates you use. So, and in the end, I will say some couple of few words about the conclusion. So we realized that the speed of this learning process depends, as I said before, this learning rate and frequency of qubit entanglement and type of spin gates used, and that maximum accuracy for photos that this network was not trained on, it means for the test set, was approximately 90%, which is not bad, considering that even the human brain sometimes cannot correctly determine the gender of a face in the photo, right? So complete replacement of the classical part of this neural network for this case of this gender recognition case has not yet succeeded due to the excessive, really excessive computational requirements if you want to simulate a variational quantum circuit with 8,000 parameters for this use case. But this is also the goal of the future work, of course, to completely replace this classical part. But it will require a truly massive deployment of a large number of GPU cores. So this is the future work, and of course, as an ultimate goal of our work is to implement a quantum neural network, or at least hybrid quantum neural network using a real QPU. But because all these results I showed you was done by using the simulator. So this is maybe everything I wanted to show you. And if you have any question, you can ask.
I have a question.
Just maybe first, let's the online speaker ask the question. Go on. Go ahead.
So may I?
Yeah.
Okay. Easy. Just two questions. Please remind me, how big was your data set of the photos, and what kind of resolution do they have?
Yeah, I was talking about, but I can.
I think that 90% is not so bad. So it's okay.
Yeah,
1,000 to
yeah,
80
it's just you can see here
1,000 faces.
400 faces. And so it's not big set maybe.
No, that's fine. I'm asking.
But the goal of our experiment was to try it, to do something and prove that it can be used. These.
No. I ask because we have the database with the malware pictures. We convert into pictures and try on normal neural network, not quantum one. So I would like to repeat it on this topic. That's why I ask you. Okay, and last question. What is your estimation with today's technologies and programming equipment? How many samples this model can process? Plus, minus.
I don't know how much. It's really.
There is capacity 1,000 faces. I see training set 1,004 faces.
Yeah, equipment you have. So
do you think 2,000, 3,000, 10,000? Any idea about capacity?
I can say, okay, we have NVIDIA GPU computational nodes here in Carolina. So I can say how long it take, how long it took, one epoch maybe. It was about about maybe 30 seconds approximately. Yeah. So it depends. So if we have yeah, but it contains also training of the classical part.
Yeah, I see.
And moreover, these qubits have been simulated. So the simulation is much more
I'm consuming. Okay, understand.
time consuming. Yeah. So
never mind.
Because the goal is to replace this classical part with the quantum part, because the real quantum part, the real quantum qubits, quantum processor in it, should be much more faster than the simulation. The simulation is, of course,
sure.
Okay,
so fine.
When we will have next year, they say we will have quantum computer. So
yes,
we can explain. We'll have 24 qubits, so there are a lot of possibilities to experiment.
Okay, thank you.
Maybe we can go to the online questions. One is, please compare the speed of a simulator versus a QPU.
Yeah, now I was talking about it.
Yeah, sorry. And
but
the second,
of course, yeah.
And the second one,
the simulation was much more time demanding.
And can someone give a rough estimate on what is best accuracy one can achieve with just classical methods?
This is the interesting question, because a lot of people think that if you have quantum computer, it means that your computations will be more precise or something. But it's not true. But it could be much more faster. That's true. And if they are faster, you can create more complex models, and you can get or achieve much more precise, with bigger accuracy results. If can someone give a rough estimate? Well, I would not do any estimates about on this. So maybe if we will have, and when we have the real quantum computer here, then we will know. But it should be much more faster, of course. Another question here.
Yeah, there was another question in the back, and please, quick question, quick answer.
Yeah, I will try. Thank you for the presentation. Like, very interesting. But here, I would be quite skeptical, or I would be afraid in this concept, basically in those like modules that you combine, the classical linear regression with this quantum machine learning combined together. And my question is like, have you checked the contributions for the final classification or for the accuracy, what is like coming from the linear part and what is coming from the quantum part? Maybe the quantum part is just like a, the donkey behind. I'm afraid so.
Okay, if I understand well, you're just asking how much, what part brings the accuracy, the information. So this is linear regression. So the role of this classical part is to lower number of inputs. So I think I did not check this. Yeah, it could be maybe interesting, but since the final goal is to replace all this linear part, this classical part with quantum part, and we prove that it's possible because we replaced, because normally there are 3 layers. They take classical layers. So we replaced in the first step, we replaced the last layer, then we replaced third and second layer. So I think it's possible to replace whole even first layer, but it depends on we don't have so good so fast hardware to do it, because it would take a lot of time, and maybe it would not be even possible, because as I wrote, it should be deployment of massive number of GPUs for this.
No. Actually, my assumption was just, what if these first 2 linear regression layers are already creating separable clusters with like 95% of accuracy, And this quantum machine learning is just adding a noise that is actually decreasing the accuracy to 90%. That's like assumption probably to be tested.
Yeah, it's maybe. Yeah, maybe it could be one of the future work, but we can see. We'll see. We will have then a real quantum hardware, and we can experiment with this, of course. But thank you for the question. Yeah.
Okay, there is a hand raised by the one Jiří.
Okay. Hello. So thank you very much for it was interesting talk. I would like to just make a sort of follow-up from previous question. Well, I would just like to ask you, so theoretically, this is like a we can say a feature reduction or dimensional reduction currently now on this part. And so this is like a ready for different type of the architecture. So we can like build up different maybe input layers, maybe we can put some skip layers, we can put some different units and then continue maybe the quantum machine learning and then maybe just filter the output. So this is like what I want to ask you, what is the biggest advantage of this approach, like beside the speeds, maybe, I don't know, this combinatorial approach or, what do you see?
The speed is main advantage.
Currently the speed.
Yeah,
so
if it's not more, there's no bigger accuracy.
Yeah. So if I put more, let's say, classical approach or deep learning to the input part, so then maybe I will just lower this speed advantage, right?
Yeah, you can do it classically, of course, but we are trying to do it in quantum way.
Yeah.
And prove the main goal of this was to prove that it's possible and it works.
I understand. Yeah. It's not a problem.
We can create many parameters, variational quantum circle with many parameters, so we can replace these.
Okay. So it means, yes. So it means that you can theoretically build up completely new direction of, let's say, neural architecture search. Yeah, if you have a real quantum computer, you can really test it, and you can basically distinguish what was maybe the previous was the previous question, that you can really distinguish what is the advantage and contribution of this classical quantum part, quantum classical, and so on. It's really nice. Yeah. So it's a completely new direction of neural architecture search. Really nice. Thanks.
Yeah. So I just want to mention that these structures here, they are one of the possibilities. You can build it in many other ways.
Yeah.
Some of these ways don't work, like this, for example. Yeah, it doesn't work. You can see. So we have to say, we just say, oh, this is not the way.
Yeah. But this is nice. Yeah, really.
We can try many other. There are a lot of possibilities, and again, maybe one last thing. Maybe
Jiří, I'm sorry, we are really late.
I should say that it depends also on the architecture of the quantum processor unit, because if we have it depends on what is a native gate, what are the native gates. So it's good to use native gates of this quantum processor and compose this variational quantum circuit from these native gates. So the performance could be much more easier and faster. So that's it. Thank you very much.
Okay, perfect. Thanks.
Yeah, thank you for your discussion. Let's thank the speaker again.
Thank you very much for your attention.
We have some delay, but we will start at 10:55 in 8 minutes with another presentation. Welcome back after a short coffee break. I would like to introduce a next speaker, who is Paulina Lewandowska. She's also a member of Quantum Computing Lab here in IT4I. She's got a PhD at the Institute of Theoretical and Applied Informatics at Polish Academy of Science. And today she will speak on quantum support vector machine in NISQ era.
Thank you for nice presenting me, Michał, and thank you all for attending on this conference. And today I will talk about the quantum support vector machine algorithm in the NISQ era. So first, a brief introduction about a classical version of SVM algorithm, this is the supervised maximum margin model, which can be used for classification our data into the label. So how the SVM algorithm classically looks like. As always, we have n elements of training data set, and let us assume that our data set has the feature. And in the simplest case, we will assume the binary classification for which our label y is equal -1 or 1. In our picture, the blue dots will be represented by the label 1, whereas the green one by the label -1. And in this algorithm, we would like to find the maximum margin hyperplane, which divides our data into these two groups. Each of, oh, it's not at work, my pointer. Oh, each of hyperplane has the formula given by the red equation, which the vector W is a normal vector, whereas the parameter B is our bias standard limit between -1 and 1. Of course, the point X, which fulfills this equation, creates our hyperplane. And it's worth noting that the sample, which are located on the margin, are called the support vector, and this is from our name of algorithm, SVM. So, if you would like to find the maximum hyperplane, maximum margin hyperplane, let us consider the two hyperplanes given by the equation H1 and H2. Then the distance between them is given by this formula. What is implies that the distance between them is equal to by the norm of the normal vector W. So if our aim is to maximize the distance, then it implies that we would like to minimize the norm of the normal of the vector W. How we can achieve it? First, we have to introduce some constraints, which are called the hard margin. Of course, to prevent the data, our point data, from falling into the margin, the blue and the green one. So the first constraint is dedicated for our blue points, whereas the second one describe the space for green points. And this constraint states that each of our data lie on the correct side on our hyperplanes. And this hard margin can be rewritten as the following inequality. However, to avoid the situation that our algorithm will be oversensitive, especially for some noisy data, we introduce the additional parameter epsilon for our constraints, which are called for now soft margin. Then, depending on the epsilon, we can decide if our point belong or not to appropriated class. So finally, if you would like to minimize the norm of this vector, we can create some optimization problem, which is exactly the minimalization of the following Lagrange function. To solve this problem, we have to create its dual problem, which is exactly the following maximization. The output of this dual problem, our parameter alpha I, for now create our decision function, exactly our classifier, exactly here, for some new data Z. Then, depending on the signal of this value, we decide if Z is given by the label -1 or 1. However, our world is non-linear, and it's not possible to meet the situation that our data can be linearly separate. So, how we can omit this problem? Of course, by using kernel trick. This is the non-linear transformation, which map our data set into some new space. In general, the larger space in which the previous space was, and then after this transformation, similarly, our decision function, our classifier has the following formula. On this example, we can see that if we have some two-dimensional data set which cannot be linearly separated, after mapping this space by using the kernel of this form, we immediately achieve the larger space, the three-dimensional Euclidean space, in which we can immediately introduce the green hyperplane. This is exactly what we would like to achieve in general. So we can see that SBM has a lot of advantage. For example, the algorithm is scalable of high-dimensional data. We can modeling non-linear data set. Moreover, by using soft margin, our algorithm is error tolerance. And moreover, we can extend this approach from binary classification into the multi-class support. So where is the problem? The problem is if we have really huge, complex, and especially noisy data set, then it's almost impossible to find the formula of such a kernel, or sometimes it's impossible to find it at all. Then we have a slow and inefficient training of our classifier. For this purpose, we can use the quantum resources for enhance our feature space. As I mentioned before, we would like to extend our space into the larger one for finding the hyperplane. And now, by using quantum resources, we can achieve the exponential larger space, especially for free, just by mapping our classical data into quantum states. As we can see, for example, on this example, so if we have some classical data located on the interval, then we can map it onto some block sphere on which we immediately determine the hyperplane described by the vector W. But for in general, if we consider our data with D feature, we use the following encoding mapping, which is also known as the quantum kernel. How we do it? We implement our classical data set into the quantum state by using this unitary gate, which can be also described as a following circuit by first using the sequence of Hadamard gates. Then we implement some unitary given by this equation, in which the choosing of this function psi, which map our d-dimensional real vector into some real number, can be chosen arbitrarily depending on our problem. And next, we repeat this circuit again to create our transformation U. Why we choose such non-intuitive kernel? It's extremely worth to note that if we choose the kernel which will be too simple, for example, if our kernel, if our circuit will be looks like kernel S, VS, ES, or VS, it can be efficiently simulate on classical computers. So it doesn't have any sense to use quantum supremacy. However, if we decided to choose kernel, for example, given by the composition of circuit SESE, this is exactly the kernel which I mentioned on the previous slide, then it's not possible to simulate this kernel in classically, then we have some promise of quantum advantage. Okay, so we have some form of kernel, so, and what next? How we can solve this problem? In the paper, supervised learning with quantum enhanced feature space, which was published around 4 years ago, they proposed two approaches. The first one is determining the kernel function, the parameter of the kernel function, by using, for example, the kernel estimation method or swap test. The second method is to omit determining the kernel, but directly determining the form of the hyperplane in the quantum feature space, in our quantum feature space by using quantum variational classification, such similar approach in which the previous speaker introduced. Okay, I will briefly explain how this method looks like. So, if we define our kernel as the following inner product, first we have to encode our vectors x into the quantum state as I introduced before. So first, the first four gates are dedicated for encoding our quantum vector, classical vector into quantum state. The second part of the circuit is for encoding some vector z. And if we create such a circuit and measure it on a computational basis, then by repeating this procedure r times, we can directly estimate the form of the kernel. But of course, it's worth noting that we have to repeat this circuit for each part of our training data set. And if we have the form of this kernel by the repetition of this circuit, then we can maximize our dual problem to obtain the necessary parameter alpha for determining our classifier. And in the next step, we use again the quantum computer for some new data from a test set to achieve the answer. The answer if we should choose the label -1 or 1. However, to achieve the epsilon precision of this method, of this kernel, we need to take at least a shot per circuit to obtain the strong precision which we would like to have. So in the one side we have exponentially larger space for let's say 3. However, the advantage started to be killing because of number of shots, which the number of circuit which we have to use. The next approach, however, use the quantum variational classification. How this algorithm looks like. As we can see of this figure, this classification task can be divided into 3 main parts. The first part is encoding our classical data into quantum state by using the previous defined unitary. This is this part. The second part is to create exactly variational quantum circuit for with some parameter theta, which we would like to optimize during our training. And finally, we would like to create some binary measurement, which will be described by the effect M. Of course, if we consider not binary classification, we will choose the different measurement. So we already know how to create the first step of this circuit. So how we create the classifier W. On the picture A, we can see the circuit by using L layers. Each of layer are creating by using first the tensor product of qubit unitary gates from SU from a special unitary group, and then we use the entanglement gate, which can be taken, for example, as on the figure B. And then we repeated this procedure L times to achieve finally the circuit with 2n times L plus 1 real parameter, which we would like to train during our algorithm. And finally, we define our measurement M, our last part of algorithm, by taking such a effect, where matrix F use the function which map our bit string obtaining from measurement to a number -1 or 1. And by taking such defined measurement, then the probability of obtaining the label while is given by this probability. Of course, by repeating this procedure r time, we achieve the empirical distribution, and based off this empirical distribution, we can assign the label while if the following inequality hold. In the opposite way, we decide to take the label -1, and that's it. Additionally, in this paper, the authors exactly create algorithm step by step how to do that. So they especially write, "Oh, please look, we have everything for testing." So what they do for training our parameter theta. For this purpose, they use the SPSA stochastic gradient descent algorithm, but this is just example. And for this purpose, for using some optimization, we need to introduce some cost function R, and we optimize our circuit while our cost function has not covered. And we repeat for each element of our training data for some fixed number of shots, our circuit which I introduced on the previous slide. By this repetition, finally, we achieve the sequence of parameter theta, which we will use on the algorithm 2. For the second phase of our classification, for some sample data S from our test set. For now, we have our optimal parameters, and then by taking some number of shots, we create again the encoding part of our new data set S by application the circuit W with our optimal parameters. And finally, we prepare the measurement, and by recording the measurement outcome from our circuit, we construct the empirical distribution for which we are able to make a decision about our classification. So the authors also create some example of this algorithm by some synthetically generated data set. And for such a data set, they proposed their encoding way. Of course, they propose also some cost function by sigmoid function. And finally, they take as final measurement the parity function. So we especially have everything for run the experiment. And what they achieve? They achieve by taking the layers which is equal 4 after 220 iteration of our SPSA algorithm, the perfect accuracy of such DeFi classification problem. Of course, we can also observe that even for the first, second, and third layer, the accuracy was up to the 90%. So it's in general quite good. However, they fulfill that this problem was solved just for data which they proposed for two-dimensional data set, which can be seen on the picture B. So what was my first task if I started my research? I wanted to implement especially this algorithm on available architecture. Of course, I will choose the NISQ, and I obtained the similar results. And the next step of my research was to extend this approach into the large spaces, at least 3, 4 qubit, to further implementation this algorithm on some real data. And what I achieved. First of all, it turns out that this algorithm can be scalable to the higher dimensional, and I obtained a really similar results for a three-dimensional data set. However, for the next step, I was consider how I can improve, how I can simplify this algorithm to a higher dimensional data set, because even if I run the experiment for qubits, I met some limitation of our time run experiment. And my first intuition is still to reduce the number of shots necessary for preparation our circuit. It can be done by taking the another cost function that especially different than the authors proposed, which this cost function should, punish for some really bad answers, and then we send the information for our algorithm. Then we are going on the wrong side. And my first initial research said that we can limit our number of sample to one-shot scenario, but it's still in progress, and this is still open question how to improve this algorithm. And thank you for your attention.
We have some time for questions. Are there any online? Can you check it, please? So maybe one inside here.
Have you tested this? Thank you for your nice talk. I have a question. Have you tested this approach the authors propose on some real life data sets? And
yes, of course.
How it behaves in that case?
Tomasz is laughing on me because yesterday I mentioned him that this algorithm, of course, works, but with accuracy around 70%, and for me it's not satisfying, so I decided to not showing you this result yet.
And what was the size of a data set you tested?
The size was around 10 sample of training set and for 4 features. So it's still not so big experiment. However, in this algorithm, we can manipulate of many feature. And for example, we can start with changing the optimizer. That's why it was my question, which the previous speaker, which optimizer the previous speaker chose, because I think that it's not problem in the quantum part of this algorithm, but with optimization method.
Okay, with this, let's thank the speaker again. And we have another break. Now it will be only 5 minutes, and we will start with the next presentation, next talk in 11:30. Thank you. Hello, after short break, we'll continue with our first foreign speaker, at least for us here in Ostrava. And he's Tomasz Rybotycki. He's a member of Scientific Computing and Information Technology Group at AstraZeneca in Poland. He did his PhD, got his PhD in 2023 at the System Research Institute of Polish Academy of Science in Warsaw. And today he will speak about automated quantum machine learning, problems, solutions, and research directions. Please, you can.
Yes. Hello, I'm Tomek, and I will do exactly that.
And yeah, actually, you probably won't be surprised because I will try to be very general in the talk, but I will actually talk about what I did jointly with Piotr Gawron about the solutions to the problem of automated quantum machine learning. And the work we have done is actually the part of Euro HPC PL project. And it was meant as a solution for non-quantum machine learning people for doing quantum machine learning experiments. So in order to do that, we had to solve some, complex automatization quantum machine learning tasks. And I will start with some short introduction to quantum machine learning, although it might be not really possible. It will, allow me to get the grip of the narration here. Then I will go through the high-level overview of the platform, and then I will jump into the inner workings of it. And but at the end, I will talk about the usage examples. We actually published a preprint as of now, but it should probably be a paper soon. You can check it on arXiv using the following QR code, and it will be also, you can get the address by the end of the presentation. Okay, so what is quantum computing or quantum machine learning? Quantum computing in general, really, is on this very simplified pictogram, you can see that what we basically do is we use the classical computer to pass the inputs, the weights, generally control what we want to do with the quantum computer. Then we use the quantum computer to do the computing, and we only get the measurement results that we then process using the classical computer. Then we update the weights and do whatever we want with them and run the experiment somehow in a loop, right? So the idea is that what we really do is we only use the quantum computer for computation and not really for any specific or very complex stuff. But in order to do the computing, we have to know how to do the computing, right? So this is actually a three-part process in a very general picture again. So what we want to do is we want to prepare the state. What you want to do then is to evolve it somehow and then get the measurements, right? But this can be even further simplified if we think of state preparation as just getting the qubits in a zero states and then using the evolution to prepare the state in a fashion that we want it to be. And then we can use this general unitary U as a general. We can think of U basically as a circuit. So it basically implements the computation that we want to do. And at the end, we measure the results and pass it to the classical computer for processing. But how does the unitary look like? In the quantum machine learning scheme, very general scheme, we'll have k layers of two different unitaries. The first unitary would be the one that we pass the input to, and the second unitary would be the one that we pass the parameter to, okay? This obviously can be identity in the either of those could be an identity matrix having nothing to do with x's or thetas. Therefore, you can think of it as the most general picture, really. This is called a data encoding layer, and it can be done also in the middle of the circuit. So that's why it occurs here in this purple block, general purple block. And this is generally implementing the computations as I told you. Okay, but right now you have to figure out what kind of encoding do you want to do and what kind of computations you want to do. And this isn't really that obvious, right? Because there are a lot of different layers for encoding, different layers for computing. So in this example, I am showing you the angle encoding. So we basically get the feature and you rotate the qubit on x-axis. Depending on the feature, here you got nearly something called not maximally entangling, but
something, and tactic layer. I don't recall the name right now, but it's basically also one of the most basic gates for the computation that were shown to do the right work. You would actually have to add another CNOT gate right here from the controlled by the last qubit to the first qubit, but that doesn't really matter. This would still be an general variational gate because we have the variational theta's. And this is one example, but it's, you know, there are a lot of those. And if you are not really into quantum machine learning or quantum computing at all, then you wouldn't really have an idea how to proceed with those, right? So that's where quantum machine learning comes in, or in particular our platform, so a Q emulator. And this is a work that is basically, the idea behind it is for it to be a black box for you. So you not only have, imagine that you only have the data, the labels, and you want to do a classification, right? So, and you want to do it in a quantum fashion. You only need to tell the platform, okay, so I've got that, do something, the platform does something, and it puts the input for you. And that's really it. That's everything you need to know. So it's basically like on this comic strip that you imagine that this is your machine learning model, you steer it a little bit and it works. So it is a little bit, you know, on a meta level, because you not only steer this pile, but also the whole, you know, garbage piles around, because it selects which one you should steer for the data to be, for the results to be useful. And it was fashioned in such a manner, our platform, I mean, so that you can use all those available quantum devices, and also include this layer that you find, or this whole sub-model that you find as a PyTorch layer, so you can you know, incorporate it into your existing machine learning model. And it is obviously fully open source according to the best open science practices. Okay, so what can it do? It can actually solve a lot of, according up to some, you know, modifications, because it was really a simple project. But what it can do, it can do classification, clustering, and multi-label classification. When it comes to you know, supervised learning, it can do linear regression. Clustering obviously being unsupervised learning. The rest is supervised learning, and so that covers a lot of standard machine learning tasks. And here's how the flow goes. The flow is that you, as a user, let me just, can I get it? Yes. So as a user, and it is, you know, this scheme is very general again, because it also assumes that you have to log into the system, that you have some queuing system. That isn't necessarily the case. Accumulator is actually a library that is available to all the users, so you can just download on your PC and you are treated as a logged user and you don't have a queue system, so the queue system. so there is that. You only pass the data, the system saves the data, and then you can pass the task. So learn for classification, for example. You enquire the task or not necessarily do so. Then the task is sent to available node or a quantum resource. And notice that it only uses the quantum resource, and quantum resource should be understood here as either simulator or a real backend hardware, whatever you pass as a device, it will be. So quantum resource is used only during that time. So you don't during the time for the computation. So you don't want to, you know, go back to the system, report something or whatever. It just, okay, I need quantum resource, ping, 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 ping. I do my stuff, and then I report all the findings to the backbone of the system. When it comes to finding the model, we actually assume that given accuracy threshold would be a precondition. And what we minimize during model finding is the usage of quantum resource, because quantum resource, right, as of now, is the one that is the most expensive, that we have the limited access to usually. Therefore, it is also an important task to be aware of how much resource do we use. And we want a model that satisfies this precondition, this, for example, accuracy or whatever score we choose. And also checks if the model is cheap to train. Okay, if we were ever to train it on a real hardware, which is not really the possible thing. Yes. So is it data valid? Yes. Propose a model, train the model, test the model. Is it the best? We save it. If no, we don't save it. We just keep the best model, and then we check if the budget is exceeded. If no, we go back to proposing another model and so on. And comparing, I mean, there are other solutions, obviously, that comes as no surprise. Only one of those solutions is open source, so I couldn't really access the other ones. So only accumulator, as to my knowledge, is the one satisfying the being able to propose a system, propose the architecture, optimize hyperparameters, and is quantum resource aware, as well as it is open source, right? So there are a lot of things that accumulator does that the other parties do not, which is, useful. And it shows how complex the platform really is and how it can help to automate the whole quantum machine learning process. Okay, but you may ask, how does it work? And this is the inner workings that I mentioned. And the inner workings are quite simple, really, because we assume in the accumulator that the most basic building blocks of quantum circuits are not really the gates, but whole layers. So we think, okay, so there were some well-known configurations of the gates, of the layers, that seem to be working in general approaches, in general problems. So why don't we try to steer them up, check if some configurations of the gates works for your given problem, and maybe we'll have something useful. And if that is the case, and you can obviously define your own layers. So there is that, but you have to have this kind of quantum computing knowledge. So that may be a little advanced stuff. But in any case, if we assume this is the only building block that we need, what we can do is we can treat the quantum architecture as a hyperparameter of our model. So we basically check whether in which order we should use we sampled the order of the layers that we want to use in our model in order to obtain the model and in order to later test it. And to do so, we can actually use the very well-known frameworks for hyperparameter optimization. So here, in this case, we use Optuna, which is, as I said, very well-known hyperparameter optimization platform with a lot of stuff that can be done with it. And we say to Optuna, okay, so find me the right ordering of the layers for my problem so that the whole model will work. And Optuna does just so. Here I want to show you the code, so how simple it is to use our platform. The code is actually taken from the unit tests of it, but it doesn't really matter because it would look exactly the same if you were to use it by code. So imagine that I want to find a classifier, quantum classifier, right? I pass the task type, so the classification. I pass the data. I pass some technical stuff, so how many cores do I have, the budget, the seeds that I want to train, so on and so on. And the only thing I do then is find me a classifier. And the accumulator just loops. Okay, this is the best classifier. Here you go. You're welcome. And that's it. That's the same goes for hyperparameter tuning. You just pass the classifier that you found or the model that you found, the data, the technical parameters. Find me the best hyperparameters for this model. And it goes loops. Those, you're welcome again. I said that accumulator is also customizable, and it is because as of now, there are two different methods of data embedding taken from PennyLane, because we use PennyLane as a main platform here. Angle embedding and amplitude embedding with some of the hyperparameters that it uses, the parameters of this function. You can obviously tweak them, but what you can also do is add another key to this dictionary, this config dictionary for data embeddings. For example, you want to check what other kinds of embedding layers are available in PennyLane. And you find something that you like, or you want to implement something by yourself. And if you do so, you just add a new position here with the default fixed arguments, and accumulator will automatically start using and trying to find the model using those additional embeddings. You can also do that for layers and other configurations. This is as simple as that. But this is the part that requires actually some knowledge in quantum computing. So it is, it kind of breaks this black box approach that I told you at the beginning. But this isn't something that you are required to do. You can just use the defaults. Okay, and just for the example, see here is this basic sklearn example of 2 moons datasets. So this is a classification task. You want to separate the blues and the reds, which is not linearly separable, so it isn't that easy. And the idea is, okay, for our platform from R to Quantum Machine Learning is, okay, find me a model, quantum model, that will allow me to separate those with, I don't know, given accuracy, for example, because we use accuracy here. And we can see, using the Optuna dashboard framework, so the one to visualize the results of training, we can see that 2 models actually were found that solved this problem. The latter being less resourceful, so used as the one returned. Here, just so you know, this is the number of trials were 10. Some of those were pruned because they didn't achieve the desired accuracy. And the accuracy threshold here was 85. Okay. We can see also if using the Optuna, which is again hyperparameter optimization framework, we can also check whether some parameters were more important than the others, and it would seem that in this example case, second layer was the most important for some reason. But there is that, you can check that. And what you can see is how you can first of all, you can only see 2 data points. That is because, as you saw, only 2 models satisfied the problem. And you can see that actually I was mistaken. The second one was less resourceful and was selected as here. The objective 0 is the number of quantum device calls. Simulators, obviously, but as I said, quantum device is everything. Okay, and the last thing. Before you jump into using accumulator, we are actually undergoing some maintenance because there were some it uses a lot of libraries inside, like the Qiskit, the PennyLane, the Optuna, and so on. And we actually are facing the issue that we are understaffed, and therefore we cannot really keep up with the changes. We are actually in the middle of including the latest update from PennyLane. Some of the functionalities may not really be working as of now, but I think by the end of next maybe 2 weeks, it should be done. Our PhD student is actually working on that, so fingers crossed. But it should be done soonish. Okay, so that's basically this. So the conclusion is that we are showing you a framework for automated quantum machine learning for not quantum machine learning practitioners or even no quantum computing people. It's based on standard libraries, so any programmer or machine learning practitioner should be able to keep up with those. And it's usable with existing quantum devices. So you can use it with Qiskit, you can use it with D-Wave, or you can use it with probably some other stuff. I would imagine IQM would work fine. Didn't test it, so I just think so. Okay, and that's basically it. You can find accumulator here and the info about me here. That's it. Thank you.
Thank you for a nice talk. Are there any questions, either online or from audience here? Yeah, please.
Hey, Thanks for the talk. I would like to ask you, like, could you elaborate more about the ansatz that has been chosen for the experiments that you've been conducting? I mean, ansatz of the loading the data for the.
Actually, I can, but I would have to go and check it in the database because I do not remember it at all.
Okay.
I would imagine it was the amplitude embedding because, as I remember, a lot of models used that were found to be useful used this amplitude embedding instead of angle embedding. But it might not necessarily be the case here because this was quite a simple circuit.
Okay, I was hoping like for some detail. Maybe I will ask you later because the thing is that depending on the embedding, we can have something that quantum computer can handle by optimizing the parameters, but then the embedding is kind of easy to solve by a classical computer, and the embeddings that are promising from the perspective of the complexity that they are providing, they are hard to optimize because for such a data as you were showing this moon data, then this kind of situations are harder for the complex embeddings that actually are promising why we are using quantum computers. Yeah.
I agree.
Okay.
I agree. So yeah, as I said, I can't really tell you right now because I do not remember, but Optuna handles or the data storage. So I have it somewhere. I just have to dig it out.
Thank you.
Any other questions? Yeah. Maybe I would like to ask for like end users of this program, how it is to somehow play with the quantum part of the program. How let's say I have something similar classification problem and I want to not use optimized or the optimally picked settings, but I would like to just play with it. Is how it work or
with the setting? You mean do you want to introduce the changes to the circuit that you have found or something else?
Yeah. For example, just to modify it, just to see the
Okay. I can tell you. When you run this find classifier, for example, it's also those kind of function here with whatever task you have in mind. What you will have in return is basically the circuit, right? So if you want to tweak with the circuit, you are very welcome to do so because you have the access to that circuit model built in some manner, right? So you have access to all the gates, order of the gates, the parameters that you have found, and you can do whatever you want with those. You can easily access it by model weights or something. It's as easy as that.
Yeah, thank you. If there are no other questions, let's thank the speaker again. And I think we can meet in like 6 minutes and we will start at 12 o'clock with last talk today.
Can you hear me?
Yes, we can.
Good.
Okay, so ladies and gentlemen, let me welcome here Piotr Gawron from Astrus and from Poland, and he will talk about the many phases of quantum computing. Please, Piotr.
Thank you for inviting me here. And first of all, I'm not longer associated with AStroSend. I am still associated with Nicolaus Copernicus Astronomical Center, which is not AStroSend. It's more complicated. And also AGH University of Krakow and Institute of Theoretical Applied Informatics of Polish Academy of Sciences, slightly. Okay, so I usually like to show this slide that computer scientists usually know about. It's Moore's law. So this is the speed up of classical computing in time. And as we can see from, there was a golden era of speed up until 2003, roughly, where we were achieving very significant speed up of factor 2 every 18 months, basically. And there was a plot. Basically, now we are in a plateau. The speed up is not longer there because we have technical problems with transistors that are too slow, too small, and they are very hot. And basically, it's not very easy to construct new transistors in fabs. So this is basically the same plot in the sense that the blue plot is the same, but a part of that we have number of logical cores, power, and number of transistors, which is important that the number of transistors grows still exponentially in CPUs. As we know now, we have like almost 200 cores per CPU, for example, so which is pretty interesting. But due to the Amdahl's law and other limitations, we know that number of transistors is not, I mean, number of cores is not giving us exponential speed up anymore. And that's a problem, of course. So, okay, here enters quantum computing. So quantum computing, of course, topic of this conference, and it's like hot topic nowadays. And there are many ways how to implement quantum computing. So there are trapped ions, which are like very interesting, and now we are working on one of ion traps now in Warsaw. There are neutron atoms. I believe Pascal is one of the examples we had contact with. Photonics chips, which are like being developed in a couple of places, Canada, China, UK, and actually in Poland we have a kind of photonic chip available now. Diamond vacancies, I don't know much about it, but I know some people from Belgium or Netherlands working on this subject. And superconducting qubits, which are the most popular qubits nowadays. Silicon quantum dots, I don't know much. And topological qubits, okay, Microsoft works on them, but nobody has seen any, I believe, yet. So there are many implementations of quantum computing, but a part of that, okay, a part of that, there are many ways we can use these quantum computers or quantum systems we have now. So I also wanted to show you the exponential, let's say, I mean, in a like common language, meaning race of the interest in quantum computing. So this is a report from European Patent Office from 2023. So it's slightly outdated, but we can see that the number of patents in the field is growing fast. So red line is baseline. So basically how many, how many patents are submitted, and the bars are in patents in quantum computing. And of course it is growing fast. I mean, I joined the hype year in 2001. So, I mean, there was very little interest in the field. And of course, that represents the hope of usually large companies that you can make money out of quantum computing. It doesn't represent physical reality, it doesn't represent technical capabilities. It is just hope and hype in a way. And similarly, there is this new topic, quantum machine learning, or artificial intelligence using quantum computing. And as we can see also, I mean, this started like 2013, 14 was the first book by late Peter Vitek, and it is growing very fast, and people are very interested in this area. Okay, I hope, I mean, I'm also interested, but we'll see whether it will work or not. Okay, and of course, I am personally hyped because we collaborate with here with Ostrava on this IQM machine that will come at some point here. So, you know, I started in 2001 when quantum computers, I mean, nobody believed that they are able to exist. I mean, they will ever exist. But now it's becoming reality, even though this computer is not going to be useful at all. And we know that. But as a research tool, it's amazing. Okay, but there are alternative computing paradigms from like the typical ones, which I wanted to talk a little bit. measurement-based quantum computing, reservoir computing, quantum walks, quantum adiabatic and annealing, and optical quantum computing. Okay, I don't know much about optical quantum computing, so I will drop it out. Quantum walks. Okay, let's. I mean that this is also dropped out, but I want to show you the couple of alternative methods, and then in details talk about. I mean some details about gate-based computing, which is like not alternative, and quantum annealing to show you how it can be done in a, let's say, more realistic scenario. So there was this idea very long ago in 2001 by Rutherford and Riegel that you can just generate a large quantum state basically using these controlled Z gates in a graph, and then perform measurements like going from left to right, and you choose your measurements depending on the outcomes of the previous result of your measurement. So you have so-called cluster states, or a complicated state on a graph, and then you just measure, 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 and measure. And this is basically the way you do your computation. And some people believe that it is an interesting model because you do not have to actually manipulate the qubits, you just measure them. I mean, there's no evolution. You prepare the state and measure. And it is equivalent to the gate model. And even like there is some interest even nowadays on this subject. The other idea, it is in general, generally in computing, is reservoir computing. So it's a really silly and also interesting idea, is that you basically, if you want to work with time series, what we do usually in neural networks, okay, we use recurrent neural networks because they are pretty natural representation of time series, and usually they don't really work so well. Sometimes, yes, but not so often. And therefore, people just looked at the dynamical systems that are nonlinear, and you basically take your data, you feed them to the dynamical system by manipulating the parameters of the system. You observe some other parameters of the system after some time, and basically from these observed parameters, you transform these the observations from, of course, many examples into expected results. So basically, this is the only step of training. This is matrix inversion in a way. And in a single step, you can transform the dynamics of the system into expected results. And these systems, it was shown, are pretty capable of simulating even complex nonlinear dynamics with just whatever, I mean, not or whatever, of course. It is important what kind of model you have here, or actual physical system, but with some basically dynamics inside. So the joke is that you can use just a bucket of water and measure the fluctuations of the within the bucket, and that's it, because it's interesting nonlinear dynamical system. So this is one of the tools, and of course people do it in various ways in the quantum setting. Usually it is done in such a way that we have an operator or a function that transforms a state in time sometime -1, and of course this transformation is usually we add some input, we remove the input from previous state, and we evolve according to some Hamiltonian, so basically some unitary evolution. And it kind of works. People, for example, in this paper, people use this kind of encoding and basically repeat the process multiple times in order to implement this reservoir model. And why not? I mean, this is an interesting model that we can study. And of course, there is this partial measurement between steps in order to learn something about the system. There is this idea also in computing that we should mimic the systems of mimic the behavior of brain by using non-digital systems in a way. So, for example, we can encode information in the intensity of impulses, like in synapses. And basically, we can manipulate these intensities. And then using some non-linear activations, we can generate outputs of from neurons that are also encoded as intensities of pulses. And this is basically a mimic, a model, like closer model to the behavior of the animal neuron. So this is one of the ideas that is around, and people do neuromorphic chips, and there is an entire field of study around it. It kind of works, but not so well. And of course, you can do a similar model. Look at the date. It's like basically these 3 days ago, Francesco Petruccione published a paper. I mean, he's a very famous professor in dynamical systems, in quantum dynamical systems and quantum machine learning. He proposed a model where basically there is a neuron composed of rotations, and then the inputs are also the activations, etc. So this is like, once again, we use quantum computers to do something interesting, silly, and different from the usual. Okay, so I wanted to go back to the gate model of computation and show you how we can go from algorithm down to the physical system. We have, I believe, slightly limited time, so I will do. I will speed up a little bit and drop error correction completely. But I want you to show what is the way, like very simplistic model of the way going from the idea of algorithm down to the implementation in the physical system. I mean, this is, of course, once again, it will be just a toy, but still I will show you how we can really program quantum computer in the gate model. Okay, so we perform computation by preparing some state in this particular problem, which is Deutsch algorithm. We apply quantum gates and then partial measurements, perform the measurement and analyze the results from the measurement. And this is basically the circuit we are going to talk about. And I'm going to explain it in more details. This is the Deutsch algorithm, like the most basic and silly and simplistic quantum algorithm, you know. So there exists. So basically the idea is that we have a binary function that is from binary to binary, and we have some quantum realization of this function. So we have this kind of circuit that implements this function. So this is, of course, we copy the input because it has to be unitary, and we have some way to obtain the value of the function. And you know, it is of course almost trivial because it's like there are only 4 functions. So for y equals 0, of course, we have this basically the value, the outcome of the function. So we assume that this circuit implements the function, and we don't know what function it is. We would like to know not the entire function by itself, but we would like to only know a single feature of this function. Whether it is balanced, it means that it has the same different values for 0 and 1, or is constant, so basically returns always 0 or always 1. And there is a nice mathematical trick that you can use, so-called phase kickoff, where just by applying the circuit from the first slide, we can encode So we start with the argument x, we go to the superposition of 0, -1. We apply the value of the function as it was shown before. So we are in the superposition. And basically, we can just rewrite this state here into this nice form so that we can see that basically the value of the function is implemented in the phase, relative phase, which is kind of important. And we have, okay, so here we have like all the implementations of these functions, I mean the 4 circuits. And we'll choose one of them to implement on a imaginary real quantum hardware. Okay, so basically that is just, okay, so there is still Polish here. I tried to remove it for. So this is basically the algorithm like in details. We have Hadamard, controlled function, Hadamard, measurement. And for constant function, we end up with state 0. For balanced function, we end up in the state 1. So of course, we measure 0, label 0 and label 1 at the end. So this is why is it interesting? Because we just learn a feature of the function and not the values. And we use quantum superposition to learn something useful, I mean, to some extent, about the function rather than just sampling it classically and having to call the function twice. We call it only once in a quantum setting. Okay, so for example, we can create a quantum circuit that implements this function. This is actually in QTIP. And we can create this circuit just by saying, okay, we have 2 qubits, one classical bit, and we implement this particular function. So f of 0 equals, I mean, that's not, yeah, f of 0 equals 1, f of 1 equals 0. And we add our gates and perform a measurement. So that's basically what we do. But, okay, this is just a program, okay, in Python. And then actually we can execute it on a quantum computer nowadays. But how it works? Usually what happens, this program is just translated into a QASM. So this is a quantum assembler, which is almost the same as the language before, at least in like there's 1-to-1 correspondence. So with the class, our register, we have our operations, we have measurements, and we have we copy the result of the measurement of a first qubit to the first bit, and that's it. So it's very simplistic, but this is the language that we use to communicate with, at some level, with quantum systems. But let's imagine that we have a quantum system that is governed by time-dependent Hamiltonian. Okay, so it's like, for a computer scientist, it's a scary word. But what it means? It means that, let's imagine that we have rotations around sigma x and sigma z available that we can implement. We control them using these hx0, hx1, hz0, etc. parameters. So assume that we can manipulate these parameters, and assume that we can manipulate this parameter j of t that governs the coupling between qubits. So if it is on, the qubits will evolve jointly. So of course, this is the element that is needed for applying some kind of controlled operation. Okay, so this is the Hamiltonian of the system. This is the physical system. So the question is now how to implement, I mean, whether it is even possible, that's one question, but here it is. How it to really implement on the physical system from just this assembly. And there is a black box, okay, there are algorithms that allow us to, okay, it's still in Polish, I mean, why? I translated it yesterday. Okay, so that allow us to generate the control program, control program that will design the sequence of impulses. So basically the values of these functions in time, this intensities of applying of operations around different axes on the qubits and couplings in time in order to implement a given assembly program. And this is quantum control theory. There are ways how to do it numerically, usually, or designed by hand. Depending on additional constraints, it's becoming more and more complicated. And of course, for real life situations, it's slightly more complicated. The question is whether this program is optimal, whether you can shorten it or not. I mean, there's plenty of questions that you can play with and to see whether you can do something fun with the quantum system. And this is needed to basically feed as controls to your device. And this device has to play with, I mean, this is how we play with devices at some, of course, abstract level. Okay, so this is basically the end of the gate model and implementation, how to go from the algorithm down to implementation. And now completely different model of computation, which is adiabatic quantum computation or quantum annealing, actually. So this is also a way we think about quantum computing nowadays, or other aspects of computing, not only quantum, because this is just a function. This is a function from strings, binary strings. In this case, plus minus 1 strings into real numbers. So we have hi, jij, some real numbers, which are somehow chosen. And si, sj are just binary variables from set minus 1 to 1. I mean, minus 1 and 1. And in principle, our goal is to find such a string as star that minimizes this function, and there is arg missing. Yeah, so argmin that minimizes this function. So this is minimum energy state. This is completely classical. And of course, this problem is very important because if you can solve this problem, you can solve many of NP, I mean, this is NP complete. So, I mean, okay, in simplifying, it is NP complete. So you can any NP problem can be expressed in such a way. And there is a very famous list of problems gathered by Andrew Lucas in Frontiers of Physics 10 years ago. And basically the usual problems that we know from computer science, discrete computing, discrete mathematics are here, like Hamiltonian cycles, coloring, and tree problems, etc. So, graph isomorphism and similar. Okay, so how quantum, I have still some errors here, sorry. How quantum computing helps us to do that? The idea is actually very simple. We take our hi and jijs, which are basically the parameters we obtain. We have to design ourselves in order to solve our classical problem. And here this weird letters are actually identities. Sorry, that there is a missing package import in the LaTeX file. But the idea is basically that we take, we translate our original problem into a quantum problem where each p now is an operator. What it means that basically, okay, given a matrix, given a basis, it is a matrix. So this is our operator, but as you heard about on the, you heard on the beginning that we are interested in energy of this kind of operators, and this is Hermitian, so the energy is real valued, and we might be basically we know that, okay, assuming that it's not degenerate, this operator has minimal energy, so minimal eigenvalue, and the associated minimal eigenvector. And it turns out if we measure this eigenvector associated to minimal eigenvalue, then we solve our original problem of Hamiltonian. Okay, so how we do it, for example, we start with a very simple Hamiltonian, and we start in the ground state of this Hamiltonian, which we can do easily. So basically, all the qubits are pointing one direction. This fully separable state. It is easy to prepare in quantum devices. I mean, to some extent. And then we slightly vary the Hamiltonian slowly from H0 to HP. So we have a linear combination of H0 and HP that we transform from one to other. And if we do it very slowly, okay, that's maybe not interesting. If we do it very slowly, we will stay in the ground state of all these subsequent Hamiltonians. So we can solve our original problem because we will end up in ground state of HP. And this is a simulation I did from with couple of qubits, 8 spins. And basically, okay, this is very boring picture because we have the initial spectrum of our H0 Hamiltonian, and then we have some random values, I mean, some chosen random values of J, I, and Hi here. And we slowly see that we achieve the ground state basically with probability 1 if we go slowly. So tau, the speed parameter, or not the speed, but slowness parameter is very high here. It's 1,000. Okay, now it's 10. Now it's 100. So if we go 10 times faster, we end up in a state that is not the lowest energy. Okay, we end up in the, this is probability distribution, of course, over the states. So we end up most likely in the lowest state, but sometimes in the higher energy state. So, okay, we have some advantage. I mean, disadvantage, but we go faster, which is important. Here we go even faster. We can see that there are some additional states that we can measure of higher energy. And we are slightly less likely to measure the desired ground state. And if we go very fast, so tau is 1 here, we are doomed. we just go away. This is assuming perfect quantum computing and no noise. If you add noise on top of that, that's becoming a little bit more complicated. But actually, people have shown that, okay, for these fast evolutions, you can obtain quantum states, quantum in quantum annulars, but for fast, not for slow, because the system decoheres. So now, and of course there are, okay, this is the old architecture of D-wave annular. So there are these quantum systems called produced by D-wave, and they have a particular topology, which is a limitation because we cannot easily embed any graph into this particular topology of connections. So there's entire like subfield of studying of embeddings. And actually, the transformation in D-wave is not linear, but doesn't really matter so much. But basically, idea is the same. And these kind of systems work. They are interesting, but not always quantum. And people still try to prove what is the quantumness of these systems. But nevertheless, there is new Advantage 2 machine that was released by D-Wave recently. I want to grab my hands on it and look at it and see whether we can obtain nice results. Supposedly, it doesn't have like plenty of qubits. It has less qubits than Advantage 1, but has better precision and coherence times. And basically, that is it. I like promote my comic book I co-authored on quantum computing, unfortunately only in Polish, quantum information mode and quantum computing, unfortunately only in Polish, but it is an open source book, so anybody can translate in any language. And if you are interested in doing this, so I can help you out with source files. And of course, this is my webpage. And thank you for your attention.
Thank you for a breathtaking talk, Piotr. And we know what we can do now. We have to download your comics to know what to read during Christmas time. So please, your questions, comments, remarks.
Thanks for the interesting presentation. I remember that when you decompose the Hamiltonian time-dependent one with this kind of decay time introduced inside, you may face a problem on the, let's say, 0+ time step. And Nipamitra in USA has demonstrated that if you don't have a zero derivative at the, let's say, first time step in time, you introduce some problem in the memory and then completely smash out the solutions. So I wonder if this would be important for this.
I don't understand what you are talking about.
Yeah, no, it's quite insight from let's say time integration of Hamiltonians, which is just I'm giving a hint that maybe there is some necessity to take care of what's happening at the very first iterations for the
Okay, at the beginning of the of the preparation of the system. Okay, but
like it has to start with zero, then starting to evolve. Like
yeah, so you have to start with the state 0.
Yeah,
What
but
you mean?
the derivative in time should be 0 as well.
Okay, so you want to. Yeah, okay, so it has to be the constant.
It has to start constant strictly.
Yeah.
Yeah, that's what I say.
Yeah.
Okay, just some comment.
Yeah, if you are not interacting, I mean, on this level of course of the modeling, we just have to have all these functions to be constant at the beginning, and then we can vary them. Obviously, this is just bank control, so 0, 1, as you could see. This is not realistic at all, and of course, you have limited frequencies. This is plenty of problems, practical problems that you can take into account, of course, once you have more detailed model of your system.
No worries.
Yeah, so
just
obviously this is just bang, very
just some hint
simplistic
that we can discuss.
No, of course, you observe because we played with real systems that produce these signals. You can see that, I mean, you would like to have envelope that is actually square, but it's not because it's a physical electronic system.
Yeah.
So it has to be taken into account, but that's something I'm just learning now when we have access to one of the physical systems.
Kind of interesting.
Physical systems, and yeah, it's an entire field of study. And of course, there's probably Lindbladian is needed rather than Hamiltonian, etc., etc. That's it.
Thank you.
More complicated.
Okay, maybe I will have one more question. You mentioned 5, I think, approaches to programming, and which one is the best one from the perspective of the power?
I mean, it's okay. Let me be very honest. It's a pointless question. What is the best? You know, we have these particular problems that you can solve with these particular methods. I mean, you can try. We have other problems that you can attack with other methods. That's the point. That there are many phases of this problem, and you know, people from hardware's level, they do whatever they can to produce the best hardware. But at the same time, you know, other people are looking into ways that this hardware could be used or maybe manipulated to implement a different model. So we don't know. This is heuristic. This is like, I mean, it also is problem dependent. I don't believe that there is like the best model for everything here.
Okay, thank you. Next questions, comment, remarks? If no, then thanks me to the speaker once again. Thank you, Piotr. So to the end, let me thanks to the speaker once again. It was a great pleasure to spend the time with you today and to listen to very beautiful talks. And I think that we have a lot of things to discuss for the future. And I would like to welcome you for the next events that Quantum Computing Lab here at IT for Innovation is going to organize. Not this year because we are at the end of the year. So next year we are planning to have a regular bi-monthly seminar And we are also assuming that we will have the same workshop in the end of the next year. So stay with us and enjoy your time. Thank you very much for coming. Bye-bye.